Today we live in a world where there are quite a few different digital FPV systems on the market. You have the likes of the DJI systems, HDZero, Avatar HD, and the slew of new Wi-Fi based systems such as this Edge T3 or the OpenIPC stuff. There is quite a lot of confusion out there of what the actual differences are between these systems from a technical standpoint, i.e. whose technology is this? Is Avatar really using DJI's technology? What is HDZero? What is the difference between Wi-Fi and all of these others? And that's what I'm going to explain today. Now, just to be clear, this is going to be a technical background dive, not talking about the feature differences and things like this. This is about giving you a history on where these systems came from, where there is overlap, where there isn't, and how they differ between each other from a wireless technical standpoint. Now, before we get into this, I want to separate them out into two distinct categories. We have Wi-Fi and Wi-Fi derived systems, and then we have custom systems. Wi-Fi and Wi-Fi derived systems are either using Wi-Fi or they are loosely based on the Wi-Fi specification, which we will talk about in a minute. And then custom systems are entirely in-house customized software and hardware, potentially even SDRs, and that's what we're going to talk about when we move on to them. It's also worth noting that there are some products that actually fall into both of these categories, such as this, the DJI Neo. This uses DJI OcuSync when you are using it with the DJI remote control, but it uses traditional Wi-Fi when you're controlling it with your smartphone. So there are some products that are able to hop between these two categories. We're going to start with Wi-Fi because this is probably the simplest end of things. But again, this is actually split into another two categories. You've got Wi-Fi systems that fully conform to the Wi-Fi specification. And then you've got Wi-Fi derived or base systems that use Wi-Fi hardware, but with modified software and drivers. However, they are technically still Wi-Fi systems. Now, products that fully utilize the Wi-Fi specification are things such as the DJI Neo here when using it with your smartphone for connection. What I mean by fully utilizing the Wi-Fi specification, this will simply set up an ad hoc hotspot. You can connect to that hotspot on your phone, your tablet, and then control the drone. Whilst you might need to use custom software from DJI to actually control the drone, the communication link on this is fully Wi-Fi. You will be able to see it on any smartphone. You would be able to detect it in the likes of Wireshark, and it fully conforms to standard Wi-Fi specifications. Just to be clear on that, that is only when using it with your smartphone. When you're using the Neo with the DJI remote controller, you then hop back into the full OcuSync system, which we will talk about a little bit more later on. There are actually two separate radios in this that it uses. It jumps between 1 and 2 for its communication, depending on the remote control system that you're using. Now, because these are based on normal Wi-Fi, it comes with all of the downsides of normal Wi-Fi, pretty poor range, and really it's designed to give you a localized control system with wide compatibility with smartphones that are available off the shelf, which means you can just grab a phone, pair it to the drone, and then you will be ready to use it. When it comes to these products here, the first thing to understand is that they are still based on Wi-Fi, but they are not conforming to the main Wi-Fi specifications. Simply think of it as one part of Wi-Fi is the pipe and another part of Wi-Fi is the contents of the pipe. Both of these products use the same pipeline. They simply pump different things through it. As a result of that, these products, whilst are using Wi-Fi hardware, are not detectable by traditional Wi-Fi means. So you're not going to be able to pick these up on your smartphone. You're not going to be able to detect these on Wireshark. These products are using modified drivers at the Mac level to be able to communicate over the link, but they are still bound by the main Wi-Fi specifications. And what I mean by that is the kind of chipsets used, like this one here, are fixed function chipsets. They're not SDRs, they're not completely reprogrammable. The hardware in these has been designed in such a way that it is designed to do a specific task. For instance, here is a block diagram of a Wi-Fi transceiver. You can see here, this is the RTL8188EUS. This is a fixed function device, so you can see it's designed to run on 2.4 gigs, has an amplifier built in, it has its dedicated hardware, you've got your baseband, that is what is creating the very core RF link that is creating the waveform. That is fixed in hardware at the PHY level. And then you've got your MAC configuration level, which your driver communicates with, which configures how it behaves within the hardware specification that it's already got. If we look at this image here in a bit more detail, this actually shows you the 802.11 protocol stack. And the thing to understand is the PHY level at the bottom down here, that's the physical level, that's the hardware, it's baked in, that can't be changed. You've then got the MAC level, this is the software level that communicates with the hardware and everything else you've got on top. And the way these Wi-Fi systems actually work is that they use a modified MAC level driver to change the way they're sending data over the link. There are elements of this that is fixed in hardware, so the frequency, the band, the channel allocations, the maximum bandwidth, the waveform itself for how the Wi-Fi is going to communicate. You can't tell it to actually create its own waveform. It is going to create a waveform that has been designed within the 802.11 specification, and all you can do is change what data and the way that data is actually encoded and sent over the link. The simplest way to think about this is it's a pipeline. The hardware is the pipe, and the contents of the hardware is determined at MAC layer and above. The pipe's diameter, the pipe's thickness, its material is all set in stone. All you can control is what you actually send through it. Now, there is a fantastic post on this from the developer of Ruby FPV on my live stream from around the 18th of May 2025. It's a live stream called I'm Back. I'm actually going to pin this post, but before I published this video, I decided to go back and add this in because it does explain things in really good detail. I'm not going to read through the whole thing here, but I will scroll through it so you can read it if you pause the video as well. And I'm just going to talk over the top of it about a few things too. So the very basics are, he goes on to talk about what they are doing with the likes of OpenIPC and Ruby FPV and even this T3 system. They are using what they call a bare metal mode, which allows them, with a modified driver, to basically take full control over the RF link in these Wi-Fi radios. They are still bound by the hardware which is used, which is the Wi-Fi hardware, but they are not restricted by many of the issues that traditional Wi-Fi brings. So for instance, packet acknowledgements, they have no issues with that. They can use whatever they want. The STBC schemes, they have a huge amount of control over the base RF link. The explanation I always use is it's using the same tunnel as traditional Wi-Fi, but they are choosing what to pump through it. And as a result of that, they have a huge amount of control, not as much control as a full SDR, obviously, but that doesn't mean it isn't capable of doing some really interesting things. So for instance, they have fully control over the Wi-Fi RF encoding. They can use whatever method to encode the data on the RF link they want. So for instance, OpenIPC uses WFBNG. That is the packet radio element. That is what is doing the RF link encoding. Ruby FPV uses its own in-house way of doing it, based, I think, on a older, earlier fork of what WFBNG is based on. You've got whatever these guys here at Edge Smart Drive are doing on the T3 system. This looks to actually be a very basic IP communication link back and forth. And the very basics are, whilst Wi-Fi isn't a full SDR, There is still a huge amount that can be done on these Wi-Fi systems, but again, they have to play within the walled garden that the hardware, the drivers allow them to, although with this bare metal mode, it does give them a lot of control. What's also interesting is many of the capabilities that DJI have are not actually just around the RF side of things. It's actually as much around their processing, their software, and again, it's about the full package that makes a system good. It's not just as simple of, is it an SDR radio or not? Is it running Linux or not? It's about the whole stack top to bottom. And whilst they are limited in these systems with regards to what they can do on the RF side, it could be as much around the software and the development of that software and how that is designed to work. So for instance, OpenIPC can be a bidirectional link, it can be a one-way link, as does Ruby FPV. It's your choice, and it's how mature the software and the link development is, even when using this bare metal injection mode, what makes the difference compared to what might be a fantastic system or what might be a system that is just okay. The kind of things that are dictated in this PHY level are frequency, bandwidth, channel allocation, data rates available. All of that is a fixed set of specification within the PHY level, and that's why these Wi-Fi systems still have to conform to things such as the Wi-Fi channel specs, the Wi-Fi bandwidths, the Wi-Fi MCS rates. Whereas with the likes of DJI, Avatar HD, and some of the others we'll talk about later, those systems are completely different. If we talk about DJI and Avatar, for instance, they are SDRs. They are entirely controllable with regards to what you want to do at pretty much every level. Yes, there are still going to be some boundaries. So for instance, its maximum frequency range, that would be determined by the design of the IC, but you're not fixed within, say, the Wi-Fi channel allocation, the waveform type. You can literally create your entire own protocol with an SDR, whereas on the Wi-Fi systems, you're in a walled garden, and whilst you can make changes, there is only so far you can go, and you can hit the limits of the main Wi-Fi hardware spec, and there's nothing more you can do about it. As for what is actually doing this, well, anything based on OpenIPC or Ruby FPV and this new Edge Smart Drive T3 Digital FPV system. These are completely different systems. There is no overlap with regards to software between OpenIPC, Ruby FPV, or this Edge system. OpenIPC actually uses WFBNG for its wireless link. This is a piece of software that handles the whole RF side of things above the hardware level. So whereas I was talking about that modified Mac driver, it does all of the communication with the hardware. It has IP Vision 4 tunneling. It handles the aggregation of the Mavlink data, dynamic FEC and radio modulation. It handles how the data is actually sent over the link. That software is basically doing the RF encoding before you get to the fixed Wi-Fi hardware. With regards to Ruby FPV, that isn't using WFBNG, that's using something else. I think it's based on a very, very old version of WFB, well, software before WFB, but they've got their entire own version of their RF encoding. And then Edge Smart Drive seem to be doing something different again. We're not fully understanding quite yet what they're doing. It actually seems quite simple and just basically tossing the video over, streaming the video over the communication link without too much going on with regards to encoding and error correction and things like that. But again, we're still trying to understand this in a bit more detail. But the very basics are, all of these are using off-the-shelf Wi-Fi hardware, but they are stuck in that Wi-Fi based walled garden. Next, moving over to the big three digital systems, DJI, Avatar HD, and HDZero. Now I'm going to start this with HDZero, and the reason for that is I don't actually have that much I can tell you because we don't know. HDZero is based on something called joint source channel coding. There is very little information out there on this. It is actually a similar technology that was used by the old Amion ProSight HD system many moons ago. Now, I've spent years reading about this, and I'm going to cheat a little bit because I'm going to use GPT to actually explain this to you because it's a bit simpler than some of the other documents that I've got. But the very basics are joint source channel coding combines two elements of the coding that you have in traditional wireless systems. You have your compression element coding of the image. That is the part that takes the massive data from the sensor, compresses it into H.264, H.265, and then you have a second stage of encoding, which is your wireless encoding. This is where you add in your forward error correction, all of the stuff needed for getting that data over the wireless link. And there are multiple stages, and if you think about a normal transmission, you have your image, you have your compression of that image, you then have your encoding of that image, your transmission, and then the reverse of it. Whereas joint source channel coding aims to combine those two encoding steps. Rather than do the image encoding and the RF encoding separately, it brings them together. Now, when you read it, it explains it here on ChatGPT. Ideal, optimize both compression and error protection jointly. The goal is to minimize end-to-end distortion, and it also reduces latency as well. And how it works is all explained here. I'm not going to go into great detail. It is still very much a bit of a black myth. We don't understand a huge amount about it. As I've said already, it is HDZero using this today. Nothing else I'm aware of in the FPV space is using this. The only other system out there that used to use something similar was Amion ProSight HD. Amion are no longer in FPV, but they do still make wireless video transmitters, and they do still make their own ASICs for them, so there's a chance they are still using that technology in that environment. HDZero uses entirely custom ASICs designed by DiviMath and HDZero themselves. There is no off-the-shelf hardware here other than some stuff around the MIPI interface and the power amplifiers. Everything else is entirely done in-house. HDZero is a one-way link. It is not bi-directional. It is a streaming system in the sense of the VTX streams video back to the ground station. There is no binding. It behaves somewhere between digital and analog in the sense of it is a digital system with analog-like behavior. It is something that we have tried for years to try and find a lot more information on, but there simply isn't that information out there. But the very basics are it streams digital video back in a similar way to how analog is line by line, but as a result of that, it can have that analog-like breakup. The sparkles, it's not quite the same, but it is similar, and that's really all there is I can tell you about it because that's all we know. But it is a digital system. It is completely custom in-house, owned by DiviMath. Next, this leaves the big two, DJI and Cadex Avatar HD. Now, before we get into these one at a time, I want to be crystal clear on something. These two systems are not the same. There are similarities in some of the hardware. There is even some heritage, some lineage, some overlap in the hardware, but they are not the same. Avatar is not a copy of DJI. DJI is not a copy of Avatar. Cadex have not stolen anyone's technology. This has its development path based on Artisan, which we'll talk about in a minute. This has its development path entirely in-house from DJI. And whilst there is some overlap in the past between DJI and Artisan, they are not the same systems and have completely separated where they were at compared to many years ago. Starting with DJI. Now, this is called OcuSync. This isn't actually their first FPV system. DJI have had many different types of wireless FPV links, which we'll talk about a little bit in a minute. They started with Wi-Fi, they moved on to Lightbridge, and then we saw the introduction of OcuSync. OcuSync is a full SDR. It is entirely custom. It is entirely in-house. And DJI even make their own ASICs for this system as well. This system obviously will use some intellectual property from other manufacturers. There are processors that have ARM cores. There are DSPs from a company called Seva. There is some core technology used that other people own, but that is the same in pretty much everything. The main thing to understand, though, is the chipsets, the software is entirely DJI's in-house design. Now, I do actually have an article on this on my FPV wiki, but it isn't 100% correct. I need to update it because there are a few things that I tried to simplify that actually confuse things. Earlier DJI products used Wi-Fi, things such as the Phantom FC40, the Phantom 2, the original one. Actually, what's interesting with DJI is they used normal Wi-Fi and then they moved to a more customized Wi-Fi, like's being used on OpenIPC and the Edge T3 system today. With the introduction of the Inspire 1, we saw Lightbridge. Now, Lightbridge was DJI's first wireless link. It is not Wi-Fi based. It is actually based on WiMAX. What's interesting, if I scroll down and show you this image here, you may recognize the name on this chip, and that is because that is Artisan. Artisan are the same company that make the chipset used today in the Avatar HD system. Just something to be clear about now, though, and I will explain this later. Artisan and DJI absolutely work together on Lightbridge. There really, though, isn't any evidence to say that Artisan had any involvement in OcuSync. OcuSync is very much a step in a different direction, and we'll talk about that a bit more in a minute. So whilst you might think, oh, DJI, Artisan, Avatar, the same, it actually isn't. There is history, but the overlap separates once we move into OcuSync. However, Artisan and DJI were working together on Lightbridge, which is based on WiMAX. For those who don't know what WiMAX was, it's basically a longer range Wi-Fi system. It's a new technology at the time designed to offer wireless broadband on the go. It never really caught on. It actually makes sense that DJI would try and base a wireless link on WiMAX because it offers point-to-point long-range wireless communication, and that is really what was needed in these systems. Now, DJI used Lightbridge in the Inspire 1, in the Phantom 3 Advanced and the Phantom 3 Pro, which launched a few months later. The Phantom 4 series, the Inspire 2 still uses Lightbridge. It's Lightbridge 2. DJI are using a customized version of the chipset, but it is still based on the same technology. It is all based on WiMAX, all centered around the Artisan chipsets. Now, towards the end of Lightbridge's life, DJI started working on something else interesting as well, and that is this down here. They started to introduce a new wireless system called OcuSync. We first actually saw this in the Mavic Pro. DJI were actually making the Mavic Pro at the same time as the Inspire 2. One of them was based on Lightbridge, one of them was based on OcuSync. They actually started testing OcuSync in the Mavic Pro and the OcuSync Digital FPV system. This was no longer based off chipsets from Artisan, and instead they were running this as an SDR off a chipset from Leadcore. Now, this chipset here is the main one. It is the LC1860 chipset. They paired it up with a separate modem, and they used this as a full SDR. Instead of it being WiMAX based on Artisan, this appears to be some entirely new in-house design, leveraging the LTE modems that are based in these chipsets. It's worth noting that whilst I have said leveraging these LTE modems, it is not LTE. DJI appeared to have very deep access to the actual hardware, and this has allowed them to basically use these chipsets as a full SDR. Think of this differently to what I was talking about earlier with those Wi-Fi based systems having still Wi-Fi based low-level hardware. These chipsets are very capable of basically being told to do whatever you want to. There are still some limitations, and again, I don't want to get too far down the rabbit hole on this one. They are based off CEVA DSPs, which allows DJI to do the encoding, the processing, and entirely create their own waveform for the RF link. There is still some inherent boundaries, obviously, but the basics are DJI was able to use these off-the-shelf chipsets to design their own entire in-house wireless link. We saw DJI use these lead core chipsets in a number of their products, and we started to even see them appear to transition to something else as time went on. And then a little bit later, we saw the introduction of DJI's first in-house chipset, which was called the P1. Now, this first appeared in the DJI Digital FPV system, the original ear unit, and the DJI FPV goggles version 1. This is actually based off much of the same core technology as this lead core chipset. The easiest way to think about this is these lead core chipsets were designed for smartphones and tablets. They had a bunch of stuff that DJI could use to make OcuSync, but they also had a bunch of stuff they didn't need as well. And the P1 is a fully customized version of that chipset. It is based on ARM cores for running Linux. It has the CEVA DSP, it has the baseband, and it's then paired up with another chipset for the RF front end that actually generates the signal and transmits. This chipset, we believe, is entirely custom from DJI, and this really did start the OcuSync journey that we're on today. This chipset was then pretty much put into everything from that point forward. Every product based on OcuSync was based on either this, the P1 chipset, or there is a smaller cut back version called the S1, which is generally used in remote controllers and a few other lower end products. It's a similar chipset, it's just cut back from a bandwidth perspective, and it has smaller cores on it from an ARM perspective. Therefore, it's not going to be able to run the same OS as the main chipset does. This new chipset has everything on board DJI need to make a digital FPV system. It has big ARM cores for running Linux. It has encoding and decoding for video processing. It has the DSP, or what is known as the RF baseband, which is all of that, but it's able to completely customize and generate its own RF waveform. And then it's got the modem, and then it's paired to an RF transceiver. This chipset basically was a complete SoC, a system on a chip. DJI run Linux on it, so the main goggles OS is on it. You've then got the RTOS for the modem, the RF system, and then you've got a second chipset, which is our RAM/ROM. So this is the ROM for storing the Linux, as well as the RAM for running Linux. And then on our second side of the board, this is paired to an IE1000. This is what appears to be a customized RF transceiver based on Imagination Technology IP. This actually allows DJI to generate the actual waveform out at the correct bandwidth. So the main chipset would create the waveform at the baseband level, and this then would generate the actual RF transmission on the desired frequency, in this case 5.8 gigs. DJI still use this chipset today. This is still used in many of their products. What's actually quite interesting when you look at the original DJI FPV ear unit is actually they designed this to be dual band capable. You can see we've got our PA and our PA on each of our antenna legs. So this side is antenna 1, this side is antenna 2. And note that there are unpopulated areas. That is because DJI designed the original FPV ear unit to actually be dual band. They just never released it dual band. They limited it to the 5 gigs band only. What's very interesting about the P1 and its little brother, the S1 that came a little later, is the fact that this became what I call DJI Crown Jewels. This became their core technology. Every product using OcuSync uses these chipsets, whether it's the P1, which is the big one, or the little brother, the S1, which is a cutback version of the P1, used either in lower range drones or in remote controllers. The S1, as I've said already, has limited bandwidth and fewer big arm cores, but other than that, it is still doing similar things to the P1. It just doesn't have the same bandwidth. So for instance, the S1 can't do 40 megahertz carrier, less antenna lanes, and again, a cheaper solution for lower range drones. What's important to understand is, without this, DJI would not have OcuSync. They then built their entire world around these new chipsets, the technology that this gave them. Think of this like Apple's A series with the iPhone. It was the beginning of Apple controlling the entire stack, and this is the same for the P1. It was the beginning of DJI controlling the entire stack from a wireless link perspective. As I've mentioned already, we do not believe this has any real heritage to the earlier technology that they used from Artisan. This appears to be that DJI went out on their own, in their own specific direction, to design their entirely own in-house link. Now, with regards to the development of OcuSync from there forward, this all gets a bit complicated. DJI continued to use the P1 in products even up until now, but they started to pair it with other chipsets to handle things such as the video encoding. For instance, on O3, DJI continued to use the P1, but rather than it doing everything like it did in the original FPV system, it now became a modem, and they offloaded the OS and the video processing onto a chipset called the E3T. This chipset had, like the P1, big arm cores for running the OS, but it had much better video encoders and decoders, and as a result of that, DJI was able to actually improve the resolution, improve the image quality, the DVR, because this processor was handling the video side of things, and then the P1 was simply left to doing the RF side of things, basically relegating it to becoming a modem. It gets a bit complicated when you start talking about what is doing what. For instance, the P1 still has its big arm cores. It's still running an OS, but it's not running the main OS. The RF side is on the RTOS, but the basics are DJI offloaded the main Linux onto the E3T, and that chipset had much better video encoders, much better video processing capabilities, DSPs, ISPs for all of that side of things, and that then was able to give us what we had with the O3 system. DJI pretty much replicated this in their drones as well. So drones like the Mavic 3, again, using the P1 for the RF side of things just as a modem, and instead actually then using a bigger chipset for handling the OS, the vision processing, and all of the other stuff. The E3T is a rather interesting chipset in itself, entirely custom in-house by DJI again. Bigger ARM cores than we saw on the P1 for running the Linux OS. Hardware, video encoders, decoders, has a VPU on board, DSPs, loads of processing capabilities on this for not only running the OS, but image vision processing as well. DJI go on to use this chipset in loads of their drones as well. They actually even run the flight control software on the E3T on some of their drones too. It's actually quite a bit underutilized in the O3 air units compared to what you see on their other products. But the very simple thing to understand is DJI added a lot more processing horsepower to the O3 system, the Goggles 2 and Integra, and that is what allowed them to improve the image quality. They were able to move from H.264 to H.265, much better DVR processing, again, because of all of the additional capabilities that this chipset had over the P1. It's hardly surprising. DJI would have designed the P1 many years earlier, and what DJI somewhat moved towards at this point was separating off the image processing from the RF side of things. Initially, they made one chipset to do both, and you actually see over time them transition to taking those two apart, having the RF on one chipset and the image and video processing in OS on another chipset. This would mean that they're no longer then limited, and that means they can pair the image processing chipset with whatever RF chipset they want, and they can switch them out as they continue to develop them over time. As I mentioned already, the P1 and its little brother, the S1, really did become DJI's crown jewels. From an FPV perspective, the V1 goggles, the V2 goggles, the DJI Air Unit and the Cadex Vista were all based off the P1, just a P1 chipset doing everything. The move to O3 with the goggles to an Integra then saw the P1 coupled to the E3T. The P1 was relegated to being a modem as such, and then the Eagle 3T was running the Linux OS, handling all of the video processing. I have used the analogy in the past of thinking about the difference between the original FPV system and O3 as DJI adding on a GPU. That isn't really the correct analogy. Basically, DJI replaced the P1's main processor with another one, ran the OS on it. That processor has much better encoding, much better image processing capabilities for the DVR, and then the P1 just became a modem, as I've said already. This leads us nicely on to O4, the latest version that we have today. If you think about the original system, everything was based on that P1 chipset, modem and video image processing. In O3, DJI separated RF and video processing, same P1 chipset for the modem, but a new chipset, the E3T, for the video processing. And with O4, whilst they have retained the E3T for video processing, what DJI actually did, if we get down to the images, is upgrade the modem. Rather than O4 using the P1, DJI introduced a new chipset called the S2. Now, if we go down to the Pro VTX, because this is the nicest one to look at, you can see here on this side of the chipset, this here is the S2. You can see it there. And this bigger chipset next to it is actually an E3T. They've just changed the labeling. Now, what DJI did with O4 was retain all of the image and video processing in OS on the E3T, but they upgraded the modem. The P1 is gone, the S2 is a replacement. The S2 transitioned from the S1. There is no P2 chipset in existence. The reason for that is DJI don't appear anymore to be making a version with the big ARM cores on to run the OS. What DJI now have decided is that this will always just be a modem. Modem is a simpler term for it, but the basics are they will now do all of the video and imaging processing on one chipset and the RF on another. And what DJI did with O4 is upgrade it with the S2. The S2 has redesigned modems, higher bandwidth capability, up to 80 megahertz carrier bandwidth, has up to 6 antenna lanes. It is still based on the same core IP, SIVA DSPs, handles all of the baseband on board just like it did on the P1, but the difference is DJI basically took the modem level a step forward at this point, and that allowed them to again improve the RF links capabilities. You can now have up to 6 antennas on an O4 based system, up to 80 megahertz carrier max now, and lots of other little tweaks beneath the hood that improved its overall performance. If we take a look at some of the other pictures, pretty much everything is the same. They still use that RF chipset, which is located under that can there. We believe it's still the IE1000, still hiding under there. You've then got your E3T here. For some reason, DJI have decided to change the labeling on their chipsets. I do wonder if it's anything to do with me publicizing it, because there aren't many people who talk about this stuff. But we've had it confirmed it's the same chipset. It's just that the labeling have changed. Might this just be that it's a different factory knocking it out? And then you've got here the S2. If we actually take a look at this in the DJI Neo, you can actually see things a little bit easier. They label the chipset the S2 in the Neo and E3T. So there it is. It's labeled the S2 there. And then if we see there, it's the E3TB. B variant, but basically the same. But overall, what DJI did with 04 was take the modem to the next step. We had the image processing step forward in 03. Now the modem has stepped forward in 04. But the very basics are that it is the same design path, same overall process. It's just that DJI are incrementally stepping their hardware forward one step at a time, whereas on the original FPV system it was just the one chip. Now DJI has that capability next time with, say, 05, of keeping the S2 as the modem and replacing the E3T with something else again if they needed it. I'm not even convinced they will even need to do that, because this really did push things a step forward. However, if they wanted to, as they are now separated, RF and processing, they can actually step them forward in any way they wish. As I've said, there's a pretty clear development path on OcuSync all the way back to the P1 and then that initial lead core chipset. With regards to DJI's earlier relationship with Artisan, as far as we can tell and as far as I understand, there is no link between OcuSync and the earlier Lightbridge system. It very much appears DJI decided to go a new direction entirely. They actually ran them in parallel at one point, and it feels like DJI didn't want to be sort of linked to, or at least under the influence of, what they could do as a result of working with Artisan. DJI wanted to create their own path, their own system that they had full control of. I'm not saying they fell out with Artisan or there was anything particularly bad there, but what it appears to be the case is that DJI decided that they wanted to fully control their own world, and that's what they did with OcuSync. There is also something very interesting when you start to look at where the IP around what DJI are using today has come from. They are using, obviously, ARM cores in their system, so they're buying in IP blocks for that. But there are also elements of their modems, such as the SIVA DSPs, that all relate back to this lead core chipset. For those who don't know, Leadcore are a company, a Chinese-based smartphone chip manufacturer that designed chipsets for smartphones and tablets. They actually did some early deals with SIVA, with Qualcomm in 2012-2013. That's where they got the original IP for making the 4G LTE modems. Leadcore seemed to vanish around 2017 and 2018, and what's interesting is, as they vanished, the likes of DJI and others seem to appear with their own chipsets with the same IP. So for instance, DJI is using the SIVA DSPs in their chipsets. They were used in the Leadcore chipsets. That's all IP acquired many years earlier. If you don't know what the SIVA DSPs are signal processors. DSPs can be used for processing image data, RF waveform processing. Basically, it's a dedicated IP block that does very complex processing for things such as signal analysis, signals, video, image processing. Think of it a bit like a dedicated AI accelerator that you see today. That is what a DSP is. The SIVA DSPs that DJI are using are RF DSPs, but there are other companies using DSPs as well from SIVA, which we will talk about in a minute. So, with regards to DJI, that's it. It is, as I've said already, entirely their world, and whilst there is some IP from other companies, that is the case in any chipset, just as it is with the likes of the Apple A series or the M series. But DJI really have created their own world here, and OcuSync is, in my opinion, one of the very best wireless technologies that is available today, and it is absolutely one of DJI's crown jewels. So, finally, moving on to the Avatar HD system from Caddx. Now, this was a system that they introduced a few years ago. It is not based on their own in-house chipsets. They are using chipsets off the shelf by a company called Artisan. Yes, this is the same Artisan that DJI used to work with that made systems based on WiMAX. Now, Artisan are again a Chinese chip maker. They actually tend to be a chip designer more than a maker, but it's clear that they do actually have their own SoCs. Today, Artisan make a lot of chips based around AI, but they also make image processors and RF chipsets as well. Their chipsets have actually been widely used in many other drones. Companies who are looking to make a drone not based on Wi-Fi and don't have their own IP will choose something like a chipset from Artisan. I believe they've been used in things from Autel and others. Their chipsets have turned up in all sorts of things, from wireless CCTV to wireless video products as well. Now, with regards to the chipset that Avatar is using, it is the Artisan AR9201. This chipset is rather similar to the P1, but it is not the same. It is not a copy. It is not a clone. There is absolutely a bit of heritage here, because just like the DJI P1 and now the S2 chipset, it is based off using a Seva DSP, but it is not even the same DSP as DJI using. In fact, the information I've been given is that they're using a DSP based off image processing, whereas DJI use a proper RF-based DSP. The Avatar system is using Artisan's hardware and software. It is still running Linux. The chipset has some big ARM cores. You can see going down, we've got the Seva DSP core. It isn't quite the same DSP as DJI are using, but again, as I mentioned earlier, remember where I said ever since lead core vanished, that IP seems to have got out. This is another example of that IP turning up in another manufacturer's chipset. When you get into it, the P1 and these chipsets from Artisan, they all do similar things. They have some big ARM cores for running the OS. They have lower, smaller ARM cores for running things like the real-time OS. You've got DSPs, you've got ISPs for image processing. These handle the baseband on board as well. So again, it's doing similar things to DJI, but it is not the same chipset. It is not the same IP, even identical. There are overlaps. They both have Seva DSPs, but they're not even the same Seva DSP. With regards to the Avatar system, the information I've been given is that Avatar is still very much got its roots in its WiMAX heritage. This is not the same as DJI. DJI isn't even LTE based. It's completely new off the base LTE hardware. Artisan knows software and past is very much WiMAX, and whilst they transitioned from fixed WiMAX hardware into an SDR, which this is just like DJI, they are still using some of their heritage WiMAX technology, whatever we want to call it. And as a result of that, that is really the big differences between what DJI is doing and what Artisan are doing. Do they have some similarities? Absolutely yes. Are they the same? No. Is it the same core IP? No. They have a history that's separated, but Artisan seem to have still gone their own way based on their WiMAX heritage. There isn't a lot more to say on this other than that their chipset has their built-in baseband, which supports up to 2 transmit, 4 receive on the main chipset. It is a full SDR, just like DJI's chipset is a full SDR as well. But their software really does seem to have its heritage in its WiMAX past. And Caddx in the Avatar HD system are using this chipset. Ignore the Xilinx reference. It was masked to try and throw people off. It is definitely using this Xilinx. It's definitely using this artisan chipset from the code. The big difference really between what Cadex are able to do in the Avatar HD system and DJI is DJI own the entire stack. So they've got their custom hardware that they've developed to do exactly what they want it to do. They've got their custom software. It's an entire SDR. They control it top to bottom. Whereas Cadex are buying in an off-the-shelf chipset, which I'm not saying is capable, because it is, but it doesn't quite have the same hardware as DJI. But they are then left to tweak the knobs that Artisan have left them, because it then has to be built off the Artisan SDK. Cadex have not completely designed their entirely own software stack on top of it. Very much most of the Avatar system is based on the Artisan SDK software. They've obviously put their own UI on the top and everything else, but the very basics are Cadex are buying in a chipset and twisting the knobs that the manufacturer has allowed them to use, rather than do what DJI are doing, is have complete customization. Now, I know there are people who've said it's a copy, it's this. It really isn't. And in the past, I've probably overplayed the similarities between the systems more than there actually is. They are as similar as an Intel CPU is to an AMD CPU. It's that simple. They both have ARM cores. They both have Siva-based DSPs, but they're not even the same DSPs. They both have an RF baseband. They both are capable of running Linux, but that doesn't make them the same. And as I've said already, the big fundamental difference here is that DJI went their own way with OcuSync entirely in-house, whereas Artisan have a very long history in wireless video based on WiMAX, and that is still very much the world they're in today. And whilst they're not using WiMAX hardware, they are still rooted in their WiMAX past, even with these new SDR-based chipsets. So in the end, what we have is a few distinct differences between the systems. DJI and Avatar HD are true SDRs, but DJI's is entirely their own in-house. Avatar HD is based off Artisan's chipset with a WiMAX heritage. We then have HDZero doing something completely different to everyone else that no one understands. And then you have your Wi-Fi systems. Again, they are not Wi-Fi as in they will communicate with your router, but they are using fixed Wi-Fi based hardware. They are not SDRs. But again, when you're using fixed function hardware that these Wi-Fi adapters have, you are always going to be constrained within the limitations of that hardware. And that is why those links don't perform like DJI does, and probably can't and never ever will. I still fundamentally believe this entire customized waveform link route that DJI have gone will never be topped. I do not think it is possible for an off-the-shelf solution with fixed hardware specifically to be able to do it. The closest thing that we got to off-the-shelf is Artisan. That is still an SDR, but again, if you look at the differences between Avatar and DJI, they are still a mile long. Even with a system that is a fully customizable SDR, it is still not able to get to where DJI is today with the likes of 04, with their custom hardware and custom software stack. Love it or hate it, DJI is absolutely the king of general FPV, but that doesn't mean that there isn't room for others. And again, HDZero are doing things that none of these systems can get near. Remember, with the HDZero system on the Nano 90, first pixel latency as low as 1 millisecond, full frame, 14 milliseconds. Nothing else comes close to this. So that doesn't mean necessarily that DJI is doing it the best way. They are absolutely doing it the best way from an image quality, I think, range and link resilience perspective. But from a latency perspective, all of these systems still suffer from that processing latency. And as a result of that, HDZero really does set themselves apart. And that is only possible due to this black magic that Carl and the team at DiviMath have done with joint source channel coding. Again, we know so little about it. It's crazy. But it's been able to do things none of these other systems have. So in the end, Wi-Fi is good. It's interesting. I still fundamentally believe it will never be as good as custom SDRs or an entire custom solution that you see here from the likes of HDZero. That's it from me on this one. I hope you found the video useful. If you have, please do let me know in the comment section. If you have any questions, put it down below. And finally, I just want to say, if you'd like to support the channel to allow me to keep making content like this, please do consider checking out the link to my Patreon as well as buy me a coffee. It is only through the support of my Patrons we're able to keep making content on this channel. And if you'd like to support us to make content in the future, please do consider checking it out. I want to say a huge thank you to all of my Patrons. We would not be able to do this without your support. Anyway, that's it from me. Stay safe. I will speak to you soon.